So in this video, I'm going to talk about something called the Rescorla-Wagner Model. Think about what's happening during acquisition of respondent conditioning. For example, Pavlov is pairing up sound plus meat, sound plus meat, sound plus meat. During that process, the CS, the sound, gains some amount of associative strength each trial, each pairing. In other words, the association builds up over time, and each trial adds a little bit of learning. But how much learning is added on each trial? How much stronger does that association grow with this particular pairing of sound plus meat on, say, trial 128? That's what Robert Rescorla and Alan Wagner created a mathematical model for back in the 70s. So the Rescorla-Wagner model is an attempt to explain the associative strength of a conditioned stimulus. In other words, how much conditioned response that CS elicits after a given amount of training. In other words, rather than just trying 30 pairings of the CS and US and seeing how well that works, we want a theory to help us understand why it takes a certain number of pairings or how much conditioned response to expect after 10 or 50 or 100 pairings of the CS and US, or how much new learning is added on, say, trial 128. So you could think of it this way. The amount of learning, the amount of change in associative strength on each individual trial relates to how far the creature is from maxing out its associative strength. So we could say kind of Vmax minus V, where Vmax just means the most this CS could ever elicit a conditioned response, the maximum amount, kind of maximum amount of learning that this CS could ever have. And V is just the current associative strength, how much that's built up already on all our previous trials. Like the previous 127 times I've paired the CS and the US before this current 128th trial. I sometimes call this the battery model. So think of the unconditioned stimulus, like Pavlov's meat, as analogous to a battery that only has so much charge to give. So if you charge one thing with it, like a sound that's paired with the meat, you'll actually have less charge left to give other things, less associative strength to then pair up, I don't know, a green light with the meat. So Vmax basically comes from how much power the US has to give, where we would say the maximum is how much response the US itself gets. In other words, how much drooling we get from the meat, that's the UR, that kind of dictates what the max will be, the max level of drooling that we could possibly get for a CS that's hooked up to the meat, right? Since that's what happens to the meat itself. So anything we associate like with meat, like a sound that we associate with meat, could at maximum get up to that amount, could get up to the UR amount. Though it might take a nearly infinite number of pairings to get exactly as much strength as the meat itself. In other words, to figure out the Vmax, you're just looking at how much total power the battery has. Start with how much a response the US gets on its own. That would be the UR, right? So Vmax will be the same strength as whatever the UR is. Whatever you get out of that much meat, that's the most you could possibly get out of things that are paired up with the meat. You can't get more drooling out of the sound than you do the meat itself. So that's where Vmax comes from. And then again, V is just how much learning you've done so far, how much associative strength you've got based on all the previous pairings you've done of your CS with the US so far. However, the amount of learning on each trial, on each of our pairings, is also going to be affected by all of the other CSs that have been showing up. The context, the background environment, things like that, that might also elicit the CR, even to a small amount. Since those have already sucked up some of the power of the battery, we actually have to subtract out that amount of power from what's available to add some learning on our new pairing, our new current pairing of US plus CS in trial 128 or whatever. The only way to know how much learning happens on trial 128 is to account for the previous 127 pairings, which is our V, but also from all the other things meat has been paired with in this creature's experience, which we'll just call V sum, the sum of all other learning, all other associations the meat has. So If simply being in the room or seeing the experimenter is also enough to elicit a little bit of salivating, that means there's a little less power available for my sound plus meat pairing. So we should subtract out V sum to see how much power is left. In other words, V max is going to be distributed across all the different CSs. So the one thing we're intending to train, that would be one, but also anything else that happens to show up with the US sometimes. So let's look at the full Rescorla-Wagner model kind of written out. First off, we are trying to predict how much learning will occur on a single trial, like the 128th time we've paired sound plus meat. So what we really want here, we want the difference between where we were on 127 versus where we're at now in 128. In other words, we want the change in associative strength on a given trial. In math, they often use the Greek letter delta. This little triangle here is a Greek letter delta to represent change in something. So we've got here delta V, meaning the change in V, the amount of learning from just this one current trial. And that is equal to all that stuff on the right. And again, what goes into calculating that? Well, look at the stuff in the parentheses first. That's what we just talked about. The amount of learning on this current trial is dictated by how much total learning is possible, V max, minus how much has come from previous pairings of this CS with the US, like those previous 127 trials. That's how much associative strength they've gotten so far. So subtract that out from the max. And then also subtract out, minus out the associative strength or the battery power that's already been hooked up to everything else that's ever shown up with the US before, which is V sum, the sum of all that stuff. But if we stopped here, the equation would basically be saying that our next trial would max things out, that it would suck up literally all the power that's left, which doesn't really make any sense. We need one more piece. We need something that tells us about the rate of power consumption from the US's battery, so to speak. Something that tells us the rate at which this particular CS will build associative strength each trial. So in the Rescorla-Wagner model, they represented that with a constant, a multiplier that ranges from 0 to 1, depending on what stimuli we're working with. We'll label it S. We'll use the label S, short for salience. Basically, if something is super salient, it really stands out to you, like if it's a super loud stimulus or a super bright stimulus, or just if it's totally new and novel to you, if you don't have any pre-exposure to it, then it will more easily get associated with the US on any given trial. So the salience is higher, right? The multiplier is closer to 1. But something that shows up with the US but happens to be super, super subtle and doesn't really stand out at all or grab your attention at all, that would make for a crappy CS, a crappy conditioned stimulus. It wouldn't stand out enough to grab much associative power on each trial. So it'd have a lower multiplier here, right? A lower S value. In other words, if you're in a room with some, floral wallpaper at the time when the US shows up, that might not stand out much at all. And the floral wallpaper then will build very little association with the unconditioned stimulus. But if someone in a giant dinosaur, blow-up dinosaur suit shows up right before the US appears, that would be much more easy to form an association with the US. It's very salient. It stands out. You'll notice it. So this here, this little equation, that's the full Rescorla-Wagner model. It's a formal mathematical way of representing how much change happens on a given trial, how much learning we get in a single trial. And what kind of results does a model like this predict if you plug numbers into this and see what happens? Well, it's basically going to imply a negatively accelerating curve. That just means a curve of associative strength, right? We're measuring how strong the association is so far. We're going to get a curve that jumps up faster in those initial pairings and actually gains less and less power per trial in each of the later pairings. It goes up slower and slower and slower after a while. So look at the graph here, and we've got V, the current associative strength between our CS and our US, how connected they are, and we see how it changes across the trials. We just get a bigger jump in trials 2 and 3 than we do in trials 10 and 11. The early trials matter more. It starts fast, during this acquisition of respondent conditioning, starts fast, lots of associative strength gained by the early pairings, but then it slows and approaches an asymptote. The asymptote would be V max. So a sort of imaginary line here, the most you could possibly get would be V max. But what about something like extinction then? Well, the model predicts a curve like this on the right here, this curve on the right with the gray bar. That's what the model predicts during extinction. We're starting out at a high level of associative strength, right? But now the CS starts showing up without the US. That means that the V max, the asymptote now will be 0, no associative strength. And V is the existing strength, which starts high. So the curve is basically just the opposite as we saw it during acquisition. In extinction, we get the biggest decrease in those early trials. In the early extinction trials, we get the biggest change, the most learning, the most extinction learning during those first few times that the CS is showing up without the US. And that model fits really well with the real world data, like what we saw before. The example from earlier that I've got on the left here, notice the acquisition phase basically has a negatively accelerating curve with biggest change in the early trials and much smaller improvements in later trials until it kind of flattens out to an asymptote. And it's hard to see on this particular blue line here for extinction, but with extinction, sure enough, we tend to get the predicted pattern where the early trials have the most drop off in associative strength, and then the later trials more slowly continue that pattern as it approaches the asymptote of 0. So yeah, there's our model. In other words, I might say, in English words, I might say the change in learning, so here's the first part, the change in learning equals how salient the stimuli are multiplied by the US's max charge available minus the CS charge so far, like this CS's charge so far, minus the total of all other CS's that have been charged so far. So this model is nice, and it's been so successful because it describes real life behavior really well, and it models it with very few free parameters and independent variables. So it's simple, it's elegant in that way, and yet still captures the phenomena we see with respondent conditioning. It generates really clear predictions and has quite a successful history of those predictions turning out correct. So it's also kind of intuitive, not just with the battery analogy, but let's just for a moment take permission to step outside the behaviorist paradigm, because usually as behaviorists, we avoid the talk of cognitive mental constructs. And for now, let's just let ourselves talk a little more casually about what's going on. We could kind of say in more casual terms that this model is about how predictive the CS is at any given time of the US. Associative strength, you could think of as just meaning predictive power, like how much you or how much your brain expects the US to show up when the CS shows up. And then the change, the delta V we talked about on each experience we have, you could think of that as kind of a function of our brain's surprise, right? I don't mean that necessarily it has to be a cognitive surprise, something we consciously think about, right? But sort of your brain's surprise as a feedback mechanism of what it didn't expect. So we're more surprised in those first few trials of acquisition when two things that have never shown up together previously start showing up together. But by the 10th or 20th or 30th trial of that same thing, we're going to be much less surprised. So you could say less learning will occur on each of those pairings. Less associative strength is gained on those later acquisition trials. They're not as new or surprising. But when extinction begins, okay, in those first few trials, the rules have changed suddenly. So of course we're going to be very surprised, or our brain is going to be very surprised in those early extinction trials. Very surprised when the US doesn't follow the CS. So we could say it makes sense that a lot of learning happens then. A lot of associative strength will go away quickly because it's a big change in those early trials. But by the time we get to the 20th or the 30th or the 40th extinction trial, well, now we're not getting that much surprise at the US not showing up after the CS, right? So we get less of a change in our associative strength each of those times, less learning on those later trials than the early extinction trials. It makes sense if you think of the brain as being set up to look for patterns in the environment. It makes sense that the brain might I don't know, pay attention when things change, when the rules change, when we're surprised and our brain's predictions aren't correct. That's what allows the brain to update its predictions, to update its model of the world, to use feedback. So more surprise means we should give this data some more serious processing, whereas minimal surprise, seeing the same thing on the 40th trial in a row, means we don't need to give it as much processing. There's not as much change to process, not as much updating to our brain's model of the world. So that's kind of the idea here and what makes the Rescorla-Wagner model so intuitive. But please do remember that the model is set up in a way that doesn't actually require us to ever talk about hypothetical mental constructs like surprise or expectation. And in fact, most behavior analysts and learning theorists think we should try to avoid such talk and stick to the observable data like behaviors and stimuli, and this equation works with just that stuff. Now, part of the reason this model is so cool is that it doesn't just explain acquisition and extinction, the basic parts of respondent conditioning. It actually makes sense of so many other effects we've talked about with respondent conditioning. For example, it explains why blocking happens. So you might recall that blocking was where once you've paired a CS with a US a lot, it becomes harder to get another CS to pair with the US. So the example I gave was the experimental design in the upper right here, where light plus shock, light plus shock, light plus shock over and over. Eventually they'll react to the light by itself. But then if we throw in a tone as well prior to the shock, doing tone and light plus shock, tone and light plus shock, tone and light plus shock, it doesn't really end up, they don't end up reacting to the tone by itself when we test it out. So that was blocking. We talked about the idea of blocking. How does that fit in with the Rescorla-Wagner model? Well, think of it as training for the CS1. That first step, the training for the CS1, was getting its V very high, right? It was getting its V level very high, charging CS1 a lot through all those trials from the battery. But that means there's not as much charge left in the battery in the US for pairing up with the CS2. In other words, when we look at how much learning happens with the tone in step 2, the new part, the CS2 in step 2, we've got to subtract out all the prior learning. So for our tone learning, we have to subtract out all the prior learning that had sucked out of the battery before. The prior learning from things like the light would go into this V sum. When we're trying to figure out what's going on with the tone, we're already subtracting out the previous light experience. So that makes sense. There's kind of some of the prior associations have taken away power that the shock has to associate with things in general. So that's why the V sum is important when you're thinking across multiple CSs. We can start to make sense of how one CS has less change or less power based on other experiences happening. That helps explain blocking. And the Rescorla-Wagner model also predicts and explains overshadowing. So remember that overshadowing was where you pair two or more stimuli up with the US at the same time, and one of them just seems to get more learning than the other. So how does this model explain overshadowing? Basically, when multiple stimuli are showing up with the US's power is split across them. Any learning for one also takes up some of the charge and has to be subtracted out in the V sum of the other one. So when we use multiple CSs paired with a US, like a light and a tone, each CS will be weaker than if it was the only CS. And this model predicts that the most salient CS, right, that's what this whole S is about, the most salient CS, the largest multiplier here, the value closer to 1 rather than 0, that would be the loudest, the brightest, the most painful CS. That'll gobble up more of that limited V max, right, gobble up faster, so there's not as much to give to the less salient CS, and also just the less salient CS will get power slower because it has a smaller multiplier here. It's not as salient, doesn't stand out as much, so it pulls power in each trial less. This just comes from that constant S at the start. It takes into account the salience of the CS and the US as well. Thus, high salience of the CS means bigger multiplication, which means more learning for this CS, and then less available for other CSs. Which isn't just intuitive, it comes directly from the S in the model. So really we could say this is a pretty powerful, elegant, and theoretically simple model that accounts for so much of what we see when we measure the learning of basically every creature we test, from snails and bees up to rats and dogs and monkeys and humans. Now, that doesn't mean the Rescorla-Wagner model is perfect or captures everything about respondent conditioning. It was created back in the 70s, and there are a few phenomena that it has trouble fully accounting for without adding some revisions, some complexities to it. Now, we're not going to go into those details, but hopefully you can start to see the use of constructing theoretical models like this, just so we can better understand and predict how learning occurs in general, or even in a fairly universal way. Anyway, this ends our videos for respondent conditioning, and after this, most of the topics in the course will actually concentrate on operant conditioning, though as we get further in, we'll start to see how the two types of conditioning work together in tandem during all of our learning all the time. So I'll see you in the next topic.